This is the first session on LLaMA model, and then we will focus on the LLaMA 1. The paper published is called Open and Efficient Foundation Language Models. So this is how I planned about the LLaMA series. The first one will be the LLaMA 1, right? So this is the paper on that, published in like a year ago. And then the second one on LLaMA 2, so it's more kind of instruction fine-tuned. And also it is trained on a larger data sets comparing to LLaMA 1. And it of course has like more like a much better performance across various benchmarks. And that is published like last July. So the next meetup, we will work through this paper of LLaMA 2. The third meetup, I'm thinking about talking about the variants of LLaMA. Since the LLaMA is kind of the foundational open source LLM right now, and there has been lots of variants that are built on top of LLaMA, such as Alpaca, Vicuna, and Lava. You see the names are all quite interesting, right, over here. So yeah, and I will show the family tree of LLaMAs next. And then the final session, I'm thinking about have a hands-on session. So basically, we can actually download a smaller model, but the smaller is like a 7 billion model, right? And then we can see how we can build a application out of that. For example, like how to fine-tune it, how to infer it, etc. So we will have some fun to really have some hands-on experience with the LLaMA model. This is the family tree of LLaMA, and I believe the family tree is continuously growing bigger and bigger. So you see like majority, like LLaMA has like 3 major branches based on what data is trained on, and also based on how the model is trained and for what applications. The big branch of the tree is for Chinese LLaMA models. So it's trained on specifically Chinese languages. And also you see here, there's various applications. For example, this is for finance. This is for laws. This is for medicine, and also same here, right? So it's specifically fine-tuned for specific domains. So this is one branch. Another branch is called Alpaca model. Alpaca model, I think, is released by Stanford, and it's trained on a synthetic data set, like further fine-tune the LLaMA model on a synthetic data set. And on top of that, it again has lots of branches, like based on what data is continuously trained, like chat data, task data, specific task data, and also with the reinforcement learning human feedbacks. The third branch, very popular one, is called Vicuna model. Vicuna model is again like fine-tune the LLaMA model on a specific chat data, so it will has better abilities to follow instructions. And also the Vicuna model on top of that, they also dive into various other types, especially this multimodal model, like this LLaMA model. Right now, it's very popular model to align the images with the existing text LLM. So over here, bottom here, you see like all of these models is multimodal models. Means that the model input can take in not only text, but also images. Usually the philosophy here is like, because it's quite expensive to train a text LLM, right? So usually they freeze the text LLM, and then they are trying to say, okay, how can I align the image representations so that it can work with the existing LLM well? So majority of the ideas in the multimodal LLM is to adapt the language representations to the existing text representations in the LLM. So when I think about like the variants of the LLaMA model in the future meetup, I will mainly talk about the Alpaca, Vicuna, and Lava models in our future meetups. So about the content, first we will basically like have a brief introduction about why like LLaMA was born. And then we will talk about approaches such as introducing the pre-training dataset, the architecture of the LLaMA model. So we have kind of more details of, okay, how the architecture differs from the original transformer model. And then we will briefly touch point on the efficient implementations of the LLaMA model. And then we will walk through the main results on various benchmark datasets. So this is a very good paper, also a very good reading paper. It's like train, compute optimal large language models. Basically, it says that like this picture over here. So x-axis is the flops. So you can think of it as the computing power you have. And the y-axis is the model size. Like basically, what's the size of the model? Like from the smaller model, just 10 million to 1 terabytes. So, and over here, so basically the question that this paper trying to answer is, what is the optimal model size given limited computing power? Right, so like there are like three hypotheses, like approach 1, 2, 3, proposed in this paper is, okay, how can we determine the model size given this computing limited computing resources they have? And then they kind of align on this linear line, saying that given this computing power, this is the best model size given these flops operations that you could possibly operate or manage on. And if you plot the like at that time, like various LLM, right, the model size and how large the data set they have been trained on. If you plot it on this curve, they find that most of the models at that time is actually off the optimal curve, optimal line over here. And the Chinchilla model is the first one, and also I think it's from Google, that they think that we should optimize the model size. It's not like that. The larger the better, but like we should like actually have an optimal model size and then train longer on existing data sets will get you even better performance. So that's how the LLaMA is trained, right? So basically the conclusion from that is current large models actually should be substantially smaller, right? So it's not always like a bigger the better. And also current large models, like for example, GPT-3 is trained should be trained much longer than is currently done. Meaning that if you shrink the model size, but you have more computing power, then you can use that additional computing power to train the models with more epochs, more iterations, to let the model see more tokens, and you would end with the better performance. And the paper also, so this sentence is from the LLaMA paper, saying that the performance of even a 7 billion model continues to improve even after seeing 1 trillion tokens. So basically, like all these models, like these models of the optimal line, they should be smaller and they should be trained longer to see more tokens to get a better performance. So that's how the LLaMA is designed. So basically the GPT-3 is like 175 billion parameters. LLaMA 13 billion is 10 times smaller size. But it's trained much longer, right? So it's trained like more iterations and more epochs. And actually the performance can beat the GPT-3. So with the smaller model, you can have a better performance on various benchmarks with the smaller model size. And the LLaMA model you see over here, so basically that's the conclusion we made, right? So with a smaller model, you can, and if it's trained longer on, say, given a fixed data set, and if it's trained longer, and actually it will outperform the performance comparing to GPT-3. So that's the conclusion of the LLaMA 1 paper. And the overview of LLaMA 1, first, it only uses public available data. so that it's compatible with the open source community, right? So what's the standards for the open source? Because you see right now, I think OpenAI faced some lawsuit from like New York Times data, right? So they think that, oh, if it's like not public data, if you use some data like not publicly available or agree on, then you may face some lawsuit. And I think that OpenAI may also have its own internal data sets, because I think they hire lots of people just to annotate the data for them. Like if since LLaMA is trained on the public available data, so it will also make it reproducible within the open source community. And an overview of the modifications to the transformer architecture. So we will see what are the major modifications to the transformer architecture, mainly the decoder architecture. And also we will see the results comparing to other LLMs on a set of standard benchmarks. So first, on the pre-training data set. So these data sets are all like a very, I would think, kind of a standard set of data sets to pre-train LLM model. So like this common crawl and also C4 data sets is all kind of crawling data set from the internet. And it's quite noisy, right? I think C4 is a cleaner versions of the common crawl. And you see like it's a really a huge data sets. And also these two data sets has the biggest proportion in the pre-training data sets. And then they also include such as like GitHub, right? So kind of have some idea about coding, Wikipedia, the world knowledge books, like literatures or scientific, and archive. So archive gives lots of information about the papers, like scientific papers. So it kind of pre-train the models to see some scientific publications. And also this Stack Exchange, so more like Q&As, right? So to get the LM have like read about how humans Q&As with each other. So this is the full pre-training data sets that LLaMA use. And all these data sets are publicly available. And after tokenization, they has about like 1.4 trillion tokens after the tokenization. So this is the sampling proportions that they used in the data sets. And this is the epochs. Epochs, you can think of it like how, on average, how many times that the token from this data set is seen. For example, like a common core is like on average, like 1.1 times is seen. While like GitHub is only like less than 1 time. Well, the Wikipedia and books, because it's like a smaller, like very small data sets, they're trying to balance the data sets a bit. So Wikipedia and books kind of are seen more times than the other data sets in the pre-training process.
Can I ask a question? So, for example, books, is the entire books data set considered here? And it just happens to be 4% of the training data? Is that how you read the table?
Yeah, that I'm not sure, like whether they have like additional filterings over here. Yeah, I don't think they have saying like detailed how they filter the data sets, but I do think they have, for example, for the common core, they only use the English language common core. So all the common core data set is English. Books, I think there will be some pre-processing steps there as well. Yeah, you can read the paper, but I didn't recall anything that they introduced, like how exactly they are doing that.
They don't specify. And specifically, since you mentioned language, for Wikipedia, they mention other alphabets as well. They mention Latin and Cyrillic. So are they just fixing on English, or is this extended for other languages as well?
LLaMA 1 is on all languages. I think it's about 20 languages, if I recall correct. So LLaMA 1 model is a multi-language model, but I would think they may not perform that well on non-English languages, but LLaMA 2 model improve a lot in the other non-English languages.
Got it. Okay,
So
thank
maybe
you.
in LLaMA 2, they will introduce more about the multilingual abilities of the model. Yeah.
But other languages needs to appear in all these data sets, right? And that's
Yeah.
Awesome. Thank you.
Great question. Next, let's look at the architecture. So if you are familiar with the transformer architecture, or even if you are not, I think I can just briefly go over that, like about what are the major components in the transformer decoder structure. So so basically this is a diagram of the architecture. It's like nearly all the LLM right now, most of them are decoder. Well, some are encoder decoder, like using the full transformer architecture, but most LLMs right now using only the decoder part of the transformer. So in the normal decoder architecture, so this is your like input tokens, means like the specific words or symbols there. And then you will put input into embedding layers, and then you get numerical vectors. In the original decoder architecture, they will apply a static positional embeddings, right? And then they take a sum to the embedding vectors. And then that the output will be the input to a stack of transformer decoder block. So the decoder parts mainly has two, I would say like two modules. Like one is the self-attention modules, like attention modules here, and then the multi-layer perception, like the densely connected layers. So in the transformer blocks, there are mainly like these two key blocks, and then the final one is like a linear mapping to predict the probabilities of the next token to be predicted. So that's a general decoder structure. Well, in the LLaMA architecture, actually they borrow ideas from multiple implementations. For example, they leverage the pre-normalization from GPT-3. They use the SwiGLU activation function from pathway language model from Google. And also they use the Rotary embeddings idea. So basically this is how it looks afterwards. It's like they will remove this. So there's no static positional embeddings. And then they apply the rope embeddings to the attention layers, which I will introduce next. And then they have this pre-normalization layers before the modules, like before the attention layers, and also they have this RMSNorm layer normalizations before the MLP module. They also change the activation function. Instead of using ReLU function, they use the SwiGLU activation functions there. So that's the major changes, and actually they borrow ideas from various sources, and this is how they think they improve the model performance. Also they use the Adam optimizer with a cosine learning rate, so that the learning rate will actually up and down during the whole training cycles. So in the next few slides, I think I will briefly talk about these three ideas. I myself find it quite interesting to understand what are these concepts and what are the major changes comparing to the standard implementations. Before diving into that, so let's look at the overall architecture, right? So LLaMA model release like multiple model sizes, like from 6 billion to 65 billions. They change the model size by changing, say, the representation dimensions, the attention heads, right, from 32 to 64, and also the number of decoder blocks, like from 32 to 80. And the learning rate, they use a small learning rate with a really large batch size. So they just use 4 million. I think it's a pretty big batch size in their pre-training process. And n tokens is how many tokens are seen in the full pre-training process. For the smaller model, they see 1 trillion tokens, and for the large model, they train to see like 1.4 trillion tokens. And this is their training loss when they are running the epochs, right? During the full pre-training process. And you can see that at some point, the model may explode, right? So the gradient explode and the models landed in a very bad place, and the loss just throws up here. And then you may need to kind of move back to the last checkpoint and then restart the training process to get over this failure, kind of pre-training failure over here. So it's quite normal, like during the training process, you will see spikes there, and then what you do is you just go back to the last checkpoint and then continue the training. So you will see that the training loss is like continuously decreasing, and they even find that it will be even more still useful, like if you train longer epochs. Actually, the performance will continuously improve. Okay, first let's look at the pre-normalization. And to understand the pre-normalization, I think we need to understand what is the difference between the layer normalization and the batch normalization. I think batch normalization is more familiar concept than layer normalization, but I think the layer normalization is proposed actually in the original transformer paper, and it's very common to use in the NLP field. So the main difference is, for example, I think it's easier to understand with example. Say you have a batch of training samples of 2 sentences, right? So in a batch, you have 2 sentences, like popcorn popped or tea steeped, etc. So this is your batch, and this is like a 1 sentence in your batch. And in the layer normalization, it will just calculate the average and variance within the sentence itself. It doesn't look across the examples within that batch, right? So for the layer normalization, the values here is normalized by this average and variance taken from this specific sentence or sequence, same over here. So that's layer normalization. For batch normalization is you normalize it against each feature dimension, and then you will just like look across all the tokens within that batch, and then you calculate the average and variance to normalize this feature. So that's the difference. Basically, the normalization dimension is different, right? So this one is you fix the batch dimension. You just normalize within the sequence. Well, this one is you fix the feature dimension, and then you normalize like across the batch tokens here. So that's a major difference. So that's a LLaMA, and what the LLaMA model proposed to use is the RMSNorm. So it's the root mean square statistics. So instead of like using the mean and the standard deviation to normalize your outputs, it proposed like we can throw away the mean. Actually, throw away the mean won't hurt the performance, and the variance is much more important than the mean. So basically, they throw away mean, and then they just do calculate the norm of the vector, and then divide it and normalize it by the norm of A. Why they do this is because they find that throwing away the average and just by standardizing by the variance, they can achieve comparable performance with the original layer norm with the mean, but it can significantly reduce the running time by 7% to 64%. depending on the architectures and the model configurations. So that's how the RMSNorm is proposed, and actually there's a paper on it. Although it's like a simple idea, but it seems there's a like a significant boost on the efficiencies of training the models. The second change is the SwiGLU activation. Talk about that, I think we need to understand GLU first. What is GLU? Is gated linear units. And to understand gated linear units, I think we can start with the rectified linear units. I think ReLU function, I guess everyone have heard about it, right? So it's like this shape, like below 0 is all 0, and above 0 is itself, right? So this shape. Like instead of using this simple ReLU, they do a linear transformation of the inputs, W, and so this is the gate. The gate, and they apply a sigmoid, right? So between 0 and 1, and then to simulate the gate function. And then they're also doing a linear transformation on the input for the values over here. And then they kind of can do the gating by element-wise multiplications between these two matrices. So this is the GLU, right? So you do a linear transformation and apply a sigmoid. So that's your gate to decide what values can be passed, or what values will be zero out, right? And then this is a linear transformation for the values. And then you do an element-wise multiplication. So that is gated linear units. I think comparing this to this simplified version is this one, there's no linear transformation, right? Like it's just like y equals x over here. Well, this one you actually learn a matrix to do the linear transformation for both gating and the value itself. So after understanding GLU, then we can understand what is this SWI in beginning, right? So switch is another function, just like sigmoid function, but it has a more flexible and also comparable shape to the ReLU shape. Right? So ReLU shape is like this line. Well, the switch function, you see that switch function actually has a very similar shape to the ReLU function. And also like by adjusting beta, kind of the parameter of the switch, you can also control like how you want the shape looks like. So basically, for this SwiGLU activation, it just changed the sigmoid function to this switch function, so that you get a more advanced function for the ReLU activation function. So they find that using the SwiGLU activation function, you can improve the performance comparing to the original ReLU function. The third major changes is the rotary embeddings or rotationary embeddings. So rotational embedding is trying to tell the model the information about the positions of the token in the sequence. Right. So just as I show in the regional architecture introduction, right? So they remove the absolute positional embeddings to add to the input embedding representations of the tokens. Instead, they add this rotational positional embeddings rope to each layers of the attention functions there. So rotation is like this, right? So say it's in 2-dimensional space. You have a vector, and then you can apply a rotationary matrix. It's like this. So suppose you want to move theta angle, right? And then you can just multiply this vector by this rotationary matrix, and then it will becomes like at a new position, kind of rotated position, right? And then you can do this many different times, like in a circle, like that. So basically the key idea is like that. You apply a rotation matrix to the vector. This is how it looks in a 2D space. And how they apply this is for all the queries and keys in the attention calculation, they apply this rotation matrix, right? So for example, this is the like queries and keys, like for each of the token, right? So for each of the token, you have like the queries and key matrix, and then you apply the rotational. I think depending on the positions of the tokens, like from 1 to 6, it will it will tell like how much angle that this vector query key is going to be rotated. And after you multiply with this rotation matrix, you will get a new query and keys that are positional encoded, because these vectors right now has the information of the positions like 1 to 2, 1 to 6, based on this rotational matrix applied. So that's the key idea under that. And yeah, so because like previous example is like a 2D rotation, right? So we know that it's just like a sine, cosine, and a 2x2 matrix. And also you can move it up to high dimensional, and actually it's a diagonal matrix. Like you can put the high dimensional rotational matrix and break it down by several sub matrices, and each sub matrix is a similar shape to this 2D rotational matrix over there. If you are interested, I think you can search for this rotary embeddings. I think it's a pretty theoretical paper to read, but I think the key idea is here is that you want your queries and keys have this rotation matrix applied so that it has these informations of where the token is sit in the sequence. And then in the LLaMA paper, they also talk about the efficient implementations. For example, how to implement the causal multi-head attention. Causal means that it only attends to the past tokens, right? So because you cannot foresee the future tokens. So they usually just call like a causal attentions, that you always attend to the tokens before you. And they have a more efficient implementation of that to reduce memory usage and runtime. And they specifically mention using the XFormers library. This is also implemented by Meta. And I look at that code GitHub page. I think it's also open source. Like it's a convenient library for you to experiment like different architectures and able to efficiently train the decode or the transformer models. They also mentioned that they reduce the amount of activations that can be avoided to be recomputed during the backwards. For example, they save the activations that are expensive to compute, especially at the final few layers of the decoder, which are the linear layers. And when they train this 65 billion model, they processes around 380 tokens per second per GPU on 2048 A100 GPUs. And training these 65 billion models to process all 1.4 trillion tokens takes approximately like 21 days. So that's the full kind of computing resources it takes to train 65 billion parameters on 2000 GPUs. So they compare this LLaMA model on about like 20 benchmarks on variety of tasks. So the first one is the common sense reasoning, just to give you an idea like what this data set is about. So this is the HELA-SWAG data set example, right? So you have a description like a woman is outside with a bucket and dog is running, trying to avoid a bus. And and you need to choose the most reasonable one, like with your common sense reasoning. like which makes sense that way. So the kind of the most reasonable answer or the next completion is the C, right? So it's kind of the multi-choice problem for this data set. So all of this is like require some common source reasoning. And then LLaMA model comparing it to like GPT-3, Chichina, pathway language model, etc. And it's able to see that the 65, at the level of the 65 billion models, I think LLaMA models can beat the performance at that time. I would say at that time because I think the development is pretty fast. I would say like as the LLaMA 1 is released, the 60 billion models LLaMA has a pretty can beat the state of the art across this common sense reasoning benchmarks. And you see that the Palm model, like 500 over 500 billion, this one can kind of has a better performance, and also this one. But the other ones, I think it has like a comparable or worse performance comparing to the LLaMA 65 billion model. The second benchmark is on closed book Q&As. So this is an example like where's the world's largest ice sheet located today, right? So without any context, then you expect the LM to grasp the general world knowledge because they may have seen this in their pre-training data sets. Right, so this is a closed book Q&As. And again, like LLaMA has the kind of shows the best performance, right? And I think one more interesting to compare is to compare the 13 billion parameters LLaMA with 175 billion GPT-3. And you can see that, yeah, I would say, yeah, I think on this data set, LLaMA 13 billion has a better performance comparing to the GPT-3. And this shot is like you provide a few examples in your prompt to the model so that the model kind of know like what type of Q&As that you are expecting from it. The evolution of the model performance during the training period, right? So this is on the benchmark data sets, right? So different data sets. And this is the performance. And x-axis is actually the training iterations, like the number of tokens seen during the pre-training process. Basically, you can evaluate all these different benchmarks with their checkpoint models, right? That is undertrained. For example, if they see just 250 billion tokens, what's the model performance on these benchmark data sets? And you see that the performance actually, the trend shows that it still can continuously improve, right? According to the trend. It means that if you train the model even longer, the performance likely to increase as well on these benchmarks. And some data sets is pretty steady, right? So you see the curve is pretty smooth. While some data sets you see it's like lots of fluctuations there, and even having a bigger model doesn't help. Like for example, I think the red one is the 65 billion. Yeah, it doesn't help on the SIQA data set. So the next one is on the reading comprehension. So this is a comprehension data set for exams. So it's like you give a passage of the English paragraphs, and then there will be like a multi-choice Q&As there, like to see whether you have fully understood that paragraph. So this is like a middle school and high school exams. And you see that the LLaMA model, it seems, have comparable performance to the pathway model, like 540 billion here. And also this math competition level problem. So it's very, I have actually, I think I can show an example here. Yeah, so it's a very complicated math problem. like for example, I ask the LLM to prove, right, like this holds. So you need to have this step-by-step reasonings of the model. And actually, it's a very challenging task here. And you see that the LLaMA model, because it's never fine-tuned on a math problem, so the performance actually is I would say it's okay comparing to like GPT-3. I think it still has better performance to comparing to GPT-3. And also you see like it even has a better performance. Like if like both the pathway models and LLaMA models are not fine-tuned for math problems, but they still can work on some of the math problems there, and you see that it can even like improve a little bit on these like huge models. 500 billion models. So yeah, and this mean I don't know how to pronounce this. Like this Minerva model. I think this model is specifically fine-tuned for math problems from Google, and you see that after fine-tuning, yeah, I think this one is a fine-tuned version of the Palm model. So it's significantly like improve the performance here. Yeah. And I think it's they also have a very cool page. Like if you search this in Google and you get to the Google research page of this model, they have a very cool page like telling about how they derive like a or develop an application, a math application based on this, and how do they do this math kind of understanding and math inference from that. So it means that for specific, like a very specialized subject, you still need to fine tune and see more math examples in order to perform well on these data sets. And same on the code generation. So LLaMA only sees the codes from GitHub, right? And actually it's a small portion in their pre-training examples. And then this is like I think the human evaluation code datasets. It's basically like you give the function name and input, and you give the descriptions and ask the model to generate the codes in yellow. So the yellow is highlighted, is model generations. And then they evaluated by what is the pass rate if you allow the model to generate 1 generation or generate 100 generations, right? Because there's like this temperature, like the model may generate like a different outputs at each time. So you give the model like either 1 time or like 100 times, and to see whether the generation output can pass the test case. And even though like LLaMA has never been specifically fine-tuned for code, and you see that it's the performance actually it's already improving or comparable to this. I think it's comparable to these 500 billion models. Means that this 60 billion is a very efficient trained on that data sets. They also evaluated on a data set called Massive Multitask Language Understanding. So it's a benchmark covers 57 subjects across a variety of topics, and also with a variety of difficulties from elementary level to advanced professional level. So there's like a STEM, humanities, social science, etc., etc. And then you see the model performance, right? Like for example, again, interesting comparison is the 13 billion comparing to the GPT-3 175 billion. So the performance actually improves mostly comparing to the GPT-3, 13 billion comparing to GPT-3. And but like LLaMA model, like if you compare it to this Palm model, right? So LLaMA model is falling behind. And one reason like the LLaMA explains in their paper is that the LLaMA model is pre-trained on a limited amount of books and academic papers. It's only like 170 gigabytes, while the Palm model is trained on up to 2T of the books. So the Palm model does see more readable books than LLaMA models, and that's where that the Palm can like scaling the model size, right, on additional data sets will help improve the performance on this specific domain subjects. But LLaMA also showed that if we are able to specifically instructionally fine-tune on these examples, then the performance also improves by a lot, right? So this is a LLaMA I is like an instruction fine-tuned. And then you can see that I think this is like 65 billion. And after a 5-shot, yeah, I think this is like after instruction fine-tuned, it's able to improve like by 5%, like from 63 to 68, and it's close to what Palm claims over here. But I think it's an unfair comparison because I don't think Palm has been instruction fine-tuned on these specific datasets. And then the last, I think, as always, every published LLM needs to evaluate their performance on the bias, toxicity, and misinformation. I think right now we all know about the Google Gemini mistake, right? So yeah, so it's pretty important to evaluate on the bias in the model generation outputs. So there's one data set called crowd S pairs, so crowdsourced stereotype pairs. For example, on the gender, right? Like it was a very important discovery where you wouldn't expect it from a female, female or a male, right? So kind of to see whether the model has preference for which statement. And again, they have using a kind of a measurement to tell the model preference over which statement across gender, religion, race, age, etc. Like these sentence pairs. Yeah, I would say this is not a very strict evaluation here, but they say that it's like the higher the score, the more bias. I would say it's just like pretty much at the same level of this, because I think LLaMA 1 hasn't been like fully focused on solving these issues. Well, it gets improved a lot in LLaMA 2. And they also claim that they expect these biases to come from the Common Core dataset, although they try to filter it multiple steps for this internet Common Core dataset. But yeah, I think the biases will just sit in this datasets, and it's hard to filter out in the beginning. Yeah, question?
So if I understand correctly, there was no, let's say, fine-tuning done after training to mitigate for these biases compared to GPT-3 and other models. Is that what the paper is
LLaMA
saying?
1, no. LLaMA 2,
No.
yes.
Okay, got it.
Yeah.
Okay. Can't wait for the results of LLaMA 2 then.
Yeah, LLaMA 1, they haven't trained any based on human preference or judgment, but LLaMA 2 has a lot more improvement on that.
Right.
Yeah.
And I know there's a huge difference between GPT-3 and 3.5, right? That it's also fine-tuned and instruction following.
Yes,
So
yes.
they don't compare
So
to 3.5, they compare
yeah,
to
so that's why I think it makes sense to compare to GPT-3, because they follow pretty much the same pre-training training process, right? So it's all like just pre-training on a set of pre-training data sets without further fine-tuning or instruction or like reinforcement learning feedback. So it's more fair comparison with GPT-3. But if you put GPT 3.5 here, yeah, GPT 3.5 well, performance will improve, but it's not fair because LLaMA hasn't taken that step yet, additional step
so
yet.
maybe LLaMA 2 would be a fair comparison against
Yes.
3.5. Okay.
Yeah, LLaMA 2 is a fair comparison to 3.5 and 4.
And the next episode. Thank you.
Yes. Yeah, but I will think, yeah, I think it's still like need to have, this is my personal opinion of dealing with this. It's more like, I think it's it require a good balance, right, of what is the world representations versus like what we think is fair and equalities, and what we hope to promote for humanity, right? I think it's a balance, because like Gemini, like Google Gemini is kind of over put too much emphasis on
Yeah.
correcting the stereotypes, while it will harm the performance of what the world actually is. So yeah, it's really tricky to manage.
I mean, either approach is fine as long as you're explicit, right? You have to say that this is based on the historical data or data I've been trained on, and this is what a potential outcome could be. Like, as long as you're very explicit, I think you're fine.
Yeah. Like evidence.
Yeah, yeah. Plus, also our own recorded data is biased, right? Let's be fair. The the history of mankind is so biased that the people who wrote those books were biased themselves, and the fact that they wrote those books comes with biases themselves. But like that comes to responsible and ethical AI, hopefully we can talk more about that later.
Yeah, I think it's yeah. Although like one direction, to have the like better and better, like even more outstanding applications coming out. But on this side, I think it's still yeah, lots of work. We can fail or lose trust in AI pretty fast
Yeah, this is
with
data
this.
driven. It's not concept driven, right? There's no way for us to describe to these models, this is the ideal world, this is how things are run ideally or done ideally. Let us know how far we are from that ideal use case, and then it could tell you. But right now, you just read a lot of papers, a lot of books, a lot of code, and it's just mirroring that.
Yeah, I think for that specific use case, it still works. It still
Yeah.
can work. Yeah. Okay, I see we are already a few minutes over. I think so. Today, I think I just want to show like I think the key idea is here is like a 13 billion, actually 13 billion model. If it's trained well enough, it can actually beat the performance of 175 model that is under trained, right? So I think that is the main message we see from this LLaMA example. So it's like, and also it shows that it's possible to achieve state-of-the-art performance just by training on publicly available data. So yeah, having additional data or curated data or private data sets help, but there's also a chance that the public open source models can have the same level of advantages comparing to these private models. And also, like, since it's open source, especially in LLaMA 2, I think LLaMA 1 not open for commercial use, only for research only, but LLaMA 2 is also open for commercial use. So it accelerates the development of RMs. Yeah, so, and they think that the LLaMA model usually, like, at the release of the LLM, they release the models at varying sizes, right? Like 7 billion, 13 billion, etc., up to 175 billion or more. And actually, I find that actually it's very helpful because, for example, we can just quickly fine tune the model or apply additional tricks to the smaller model first, like on the 7 billion model first, so that we can experiment with it and also to see whether it could potentially work. And then once we figure out how to make it work, we can scale up the model size to 175 billion. So I think it's still very important to release a smaller size models, right? For the development and also for the research purpose to experiment with different ideas, or else it's too costly to always play with that large size. And I think the LLaMA has their codes published because it's open source. So it's on the Facebook Research LLaMA. And also looking at it is very interesting to see how they implement, for example, the RMS layered norm and all the other rotationary embeddings, etc. So you can actually see how that is calculated in codes. So I think I will keep it to the last session. Well, I may show some examples there, although I don't think, unless you want to modify and experiment it, then but for building applications, I don't think it's helpful. This is just for the purpose of interest and learning. And then we will see how we can load the model and fine tune it. Yeah, so stay tuned for the upcoming sessions. So LLaMA 2 next, probably in 3 weeks, the LLaMA 2. And then we will have the look into the families of LLaMA and have a hands-on session on that.